Okay, this is chapter 3. So in the chapter 2, we give some like basic understanding about the bonds of the structure. And that is important because the material property is heavily depends on how the bonding is. And when you have the bond, then depends on the material, the bond might have a different way of the arrangement. So in here, we are going to look and actually going to focus on the solid. And this solid is what we call the crystalline solids. We want to know what are the different ways the atom can arrange. And there's a terminology called the crystalline and non-crystalline, which you can read from the book. I'm not going to repeat those things. And we are also going to look at how people actually name these different kind of crystal structure. In the textbook, there's a table to show you what a different kind of a crystal structure categories. We are only going to focus on several of them. Okay, there's so many of them, but the fundamental one are the thing that we're going to look at. And that is the focus of this Friday's lab. And the next point is also an important point, which is this one here. This one is also known as the Miller's indices. So we will look at how we name the points, the direction, and the planes. So in a crystal structure, we do have a way to specify those things. So you have to learn how to specify those things. In your first exam, you're going to have a question about these things. So make sure that you understand that. So we'll put focus on the crystal structure. We'll put the focus on the point, direction, and planes. And if we have time, we will also look at the X-ray diffraction. If done, then we will look at that on the Thursday. I'm going to give you some example, use the example to describe how you can use the X diffraction to identify the elements. There's another calculation that we would do is that how can you actually calculate the theoretical density of the material just based on the crystal structure of the material. So these are the things that we are going to look at. Okay, so in the lecture video that you will hear Professor Wang talk about these things, I just briefly go through this. So the more detailed thing that you can read is from textbook. So you might have an atom not packed, like very random arranged, like this one here. And in the previous chapter, we look at the energy of the atom, and the energy will have the minimum when they are most close packed, which means they have the most stable arrangement. When that is the case, then you have the lowest energy, which is the most stable energy. If they are not in a stable energy, then most likely the energy will increase. So the dense ordered packing is the stable one. When that is the case, then the location of the lowest energy is the bond energy between the atoms, and then you're going to get this kind of a picture. In our case, we are more focused on the dense packing. So ordered structure will have the nearest the minimum in bonding energy, and they are more stable. So that's the conclusion from these two pictures. And there's a crystalline, there's a non-crystalline, which you can read from the textbook. I'm going to skip this part, just no idea about that. And another name for the non-crystalline is amorphous. So the amorphous is also the same as the non-crystalline. Then for the crystal structure of the metal, they are more like dense atomic packing. So they try to arrange so they are more stable. If they are not stable, then they will have a reaction, so they're going to change to some other things. So most of the time when we look at the metal, is going to be the crystal structure, and that's the main focus of this chapter. So on Friday, we're going to start with this structure. This structure is called the simple cubic. and abbreviation is the SC. It's a simple cubic, but it's also non-ideal. Very, very rare. You're going to have the metal arranged in this way. And there's certain reasons. So once you go through the Friday slab, then you will know. And the simple qubit is that you just have one atom on top of another atom, and at the bottom will be the same atom at the bottom. So on the very right, which you look at this one here, wow. Sorry. Just go back. I'm trying to get a pen here. So on this one here, which is an arrangement of the same atom, but they are in several different layers. So they arrange in three-dimensional way and go in all directions. Each one of the dots represent an atom. It's just a strength version of the atom. If we separate this structure to the simplest, smallest repeated cell, that is what we call the unit cell. So the unit cell is the smallest repeated entity of the structure. And you can simply cut the 4 atoms on the top and 4 atoms at the bottom to get this one here. So these two are the same thing, but on the right hand side is just the smaller version of the left hand side. We just use the dots to represent the whole atom. And as you can see from this one here, if you wanted to know the density, and it's very obvious that you simply look at how many of the space actually occupied by the atom. And what is the total number of the atom in that qubit cell? Because the number of the atom in that volume represent how much of the mass that is going to be in that unit cell. So you can get the volume by looking at this unit cell, and you can look at how many space occupied by the atom to calculate how much of the mass there are inside of this unit cell. Then we can calculate the density. So one of the first calculation problem in this chapter is that if you know the structure of the atom, can you calculate what is the theoretical density of this elements or this metal? And you're going to see in the slide, they're going to show you an example. In the lab, we're going to practice to identify several terminologies here. One is so-called the coordination number. In your previous lab, you were using the coordination number. I can't tell you what coordination number is. It's the number of the nearest atom touched to the other one. So if you have an atom in the center, how many atoms right next to you touch to you? And that is the coordination number. So that's how we define a coordination number. And how do you identify that? You have to look at the structure. And the tomorrow's lab, you're going to calculate this one here, which is what we call the atomic packing factor. This is more similar to like the density of an element. It tells you how dense the volume to be occupied by the atom. And the way to calculate that is to find out what is the total volume of the atom in a unit cell. Remember, the unit cell is the smallest repeated entities in your crystal structure. So you find a unit cell and you count the number of the atom inside of the unit cell. Now, when you counting it, most of the time they're not like always like a full atom inside the unit cell. Just like the previous one, when you look at that, right? These one here, they are just how many of this, like what is the portion of the atom of this corner over here? It's not half, it's not quarter, it's like a 1/8, because you're cutting a circle by 3 ways, X and Y and Z. You cut it in half and half and half. So it's 1/8 of an atom. And how many do you have? You have 4 on the top, 4 at the bottom. You have 8, a 1/8 of atom in total in this cubic. That means 8 times 1/8, that is equal to 1. So in total, even though it doesn't look like a 1 atom in a cell, it actually is 1 atom in a cell. So by knowing the volume of each one of the atom, and also by knowing the volume of the unit cell, then you can kind of know by volume what is the density of that. And that's what we call atomic packing factor. Different arrangement will have a different number, and how do you do the calculation is the topic of Friday. So I'm not going to repeat that at here. When we go to the Friday's lab, you're going to put a decent amount of time to actually figure it out and learn it. And this is important because this will tells us how the radius of the element, which is this one here, related to the unit cell length. A here represents the lattice length, and you probably hear about this terminology in your previous lab. R is the radius of the atom. So radius of the atom, the lattice length, how are they related depends on the crystal structure. And here is how we count the total number of the atom, just like I told you before. How do you count that? You have to find out in each corner how much of the atom actually occupy each one of the corner and how many of them are. The next one is another structure. This is more realistic. More of the atom is like a BCC. This is called a BCC because there's a body at the center, which is this one here. This one is the center of the cubic cell. And the next one is, so you are going to look at this, this structure, and you will find a different way to relate the radius and also the lattice length A. And the last one, well, this is not the last one, actually, there's another one. So the next one is the FCC. FCC is the face center, meaning on each one of the face, you're going to have an atom with the center to be the atom. So this is, so this one is the face of an of a unit cell, and the center of the atom is going to be right on the surface. That's why this is a face center cubic structure. So that is the next structure that you're going to study on Friday. You're going to do the similar thing to find out how this R is related to the A, and just look at the geometry and look at where is the line each one of the atom is going to touch with each other, because you don't know the space between here, let's say, between here and here. I don't know how much space that is. All I know is that if they touch with each other, this one will be the radius. This will be 2 times of the radius. This will be the radius. So this is actually how you're going to find out how to relate the radius with the lattice length, the A. You can also calculate the APF, use the same formula that we showed you before. So that, again, this will be the focus on Friday's lab. So I'm not going to repeat that at here. Now, the last one is so-called HCP, and it's very similar to the FCC. It is hard to draw the difference, and it's even hard to look at this picture that shows you on the slide. It is best to show in a three-dimensional, so the bottom picture actually shows better to see what the FCC is. To count the number of the cell, it probably is the best to show in another way. Now, this one is called the HCP. It's a hexagonal closed pack structure. If you look on the left-hand side, that left-hand side is a representation of how the atom is arranged in three different layers. And the A layer and the bottom layer, the top layer, bottom layer, actually arrange the same way. The middle layer will have the atom just right in between the space of the top and the lower layer. So they kind of located at the center of that. You're not putting the atom on top of another atom. You put the middle atom to be inside of the curve of three or four different atoms at the bottom or on the top. So that is what we call the HCP. Now, this structure shows you doesn't represent one unit cell. This actually represents 3 unit cell. Now, 1 unit cell for this one is this. If you wanted to see the unit cell for this situation, this is the unit cell. So if you cut this one out, and this one represents 1 unit cell. So for this one here, actually represents 3 unit cell. You have another one at here. You have another one at here. So there are 3. 1, 2, and 3. 3 unit cell in this case. Okay, so in the lab, again, we are going to do the calculation for each one of the structure. One of the calculation you have to do for your homework is to find out what is the theoretical density for a metal. Now, the metal, most of them will be either like BCC, FCC, or HCP. To find out the density, you need to know what is the unit cell. So how do you define a unit cell? So unit cell is the smallest repeated entity in the crystal structure. So you had to find out how they repeat with each other and what is the smallest one that is repeated all the time. So that one, let's say you find out the unit cell at here. So this will be your unit cell. And to find the density, our density is defined by the mass over the volume, right? Mass over the volume. The volume is very simple. If you know the length of this, and if this is a cubic, then the volume of this is simply just equal to a cube, right? This is the total volume. But what about the mass? Well, the mass has to depend on how many atoms that you actually fit into this unit cell. If I just make an assumption, just make a very simple assumption. Let's say I only have like 1 atom inside of this unit cell. Then I need to determine how much of the mass of this 1 atom, of this element, right? If they give you this is a gold, then you look at the periodic table, you can find atomic mass. The atomic mass is the mass of 1 Avogadro number of atoms. So it's not a single atom. You have to take into account of the Avogadro number. That's why in this equation, you see this number over here. So this A represents atomic weight. You divide by the Avogadro number represent the mass of single atom. So A divided by MA is the mass of a single atom. N represent how many atoms in the unit cell. Then you get the total mass inside of the unit cell, right? Then you divide by the volume of the unit cell. That is how you get the density of an element. Here they show you an example. Again, you can watch the video to understand this. There's an example in the textbook as well. So look at that to understand how to do this calculation. That's not very complicated, but the first thing you have to know is they must tell you what is the structure of that element. And also, by knowing the structure of the element, you will be able to know the radius and the A, because that determines the volume of the unit cell. That determines what is the atomic mass of the atom inside of that element. So this will be one thing that you need to know, and make sure that you know how to do the calculation on this. The book also talk about the single crystal and the polycrystalline materials. So single crystal meaning the whole object is made of one single crystal, which is very difficult. Think about the chip that you purchase from the market. Those are like a silicone chip, and they are made of the silicone waffle. Why this one is a high-tech industry? Because it's hard to make a pure element. You wanted to make a pure silicone waffle, it's very, very hard. You have to make the environment very, very clean. So single crystal is hard to find. Most of the time, you're going to see this like a polycrystalline material. The grain size are keep on changing, and because their arrangement, their orientation are different, and most of the time they're purely just random. Okay, that's the most common thing that you're going to see in the reality. Why do we talk about this? Because the material, when you are using the material strength might depend on the direction. If you have a material strength, the material property depends on the direction. That's what we call the anisotropic. If it doesn't depend on the direction, it's called the isotropic. Okay, so just get an idea about this. If you have a polycrystalline, because the polycrystals, they have a grain inside of the material oriented in all directions. So the total sum of those properties will also randomly arranged. So the property may be like isotropic, which means it doesn't matter which orientation that you are using the material. You don't really care about what's inside of the material, how they arrange with each other. They're going to give you about the same property. But sometimes if you have isotropic material, then you have to be careful. Then the direction matters. Then how do you put the object will change the property of the material. Okay, the next important topic for this chapter is this one here. This is also known as the Miller's indices. So Miller's indices is this. The purpose of creating this indices is to specify the material's position, the direction, and the plane. Okay, the position, direction, and plane. Because material might be stronger in certain direction. It might be moving at a certain plane. And in order to identify those, we have to categorize those things. And that's why people try to define a way to like specify what is the direction and what is the plan, what does that plan means. So here, this part, you need to actually do some homework to understand how to define those things. Okay, so on Friday we're gonna not Friday, on Thursday we are going to do some example of these. Just make sure that you know how to do this. And again, in the exam, you definitely going to have problem about this topic. We are going to give you some structure, ask you to define the plan, the direction based on the structure. Let me give you some idea how we do this. There's an example in the textbook as well. So let's start with the point. Point is more like a coordinate. The first thing you do when you are given with a structure, then you have to find an origin, right? Origin is defined by humans, so you can define any point as your origin. In this case, when you look at the slide, we have origin, which is at the intersection of the x, y, and z. So here is the origin of our definition of the coordinate. If you have a point in the space where the point is this point at here, how do we define this point? Well, if you use the way that you learn in the math or in the physics, then we always define this point by looking at what is the positive, what is the negative, right? So I have x is going to this 45 degree to the left. Actually, that represents going out of the plane. Y go horizontally, z go vertically. So the coordinate of this point, or the point A, is going to be 1 unit to out of the paper, 1 unit to the right, 1 unit to the top. But we don't write 1, 1, 1. Instead, we write 1, 1, 1, like this one here. Okay, we don't put comma. Okay, we don't put comma. This is just a convention when we define the coordinate of a point, and we use 3 digits. That 3 digits represent the length of that position. How much does it further away from the origin? And that's the length, the age length of that. We don't put space, we don't put comma, we just write these 3 digits. Okay, remember this. This is different than what you write as a coordinate. And what about direction? Well, if you wanted to find direction, you need 2 points, right? You need to find 2-point coordinate. So in this case, in this picture shows you we define point 1. In the red color, we define the second point, more like a purple color or the blue color. And then you have to find what is the direction. So how do we define the direction? Well, to find a direction, we have several steps. The first step is only just find the 2 points. So we find 2 points by write down the point coordinate. Remember, point coordinate, you don't put comma, you don't put space. So if I wanted to find a point 1, what is my point 1? And point 1 is going to be a 0, 0, and 0. So this is my point 1. What about point 2? Well, if the length of here is 1, then the point at here is what? It's not 1 unit, it's actually half of the unit. So how do I write the coordinate of this point? Well, the first thing you look at is how far is it away from the origin in the x direction? Well, that is 1. What about y? It's Are there any movement along the y direction? No, actually it's going to be 0. Are there any movement on the z direction? Yes, it moved up, but it's not moving up for the 1 unit, it's 1/2 unit. Okay, so you have a 1, 0, 1/2 for the point 2. Now, when we define the direction, we use the final point or the half point minus the tail point. So if I do the subtraction, which is this one here, this step over here, the first step is to find the point coordinate. Then the second step is to do this subtraction. Then I have 1 minus 0, right? This is the first point. The second point is the 0 minus 0. This is the second point. And the third point is 1/2 minus 0. So this gives me 1 and 0 and 1/2. Now, when we define direction or we define a plane, we don't use rational number. We like the whole number. So you're going to find the smallest whole number by multiply a smallest integer number to make it all equal to a whole number. So what is the number that we should multiply with this one here? Well, if we multiply by 2, then I got a number which is a 2, 0, and 1. So when we define the direction, and we got this direction, which is 2, 0, 1. Okay. Again, we don't really put, the comma or space, but how do we know this is not the coordinate point, this is the direction? Well, another rule. The rule is use the square bracket for direction. If you don't put any of the bracket, then it's just a coordinate. If you put a square bracket, it represents a direction. So direction, use the square bracket. That's why we use this one to represent this direction. Okay, now let's do another example. Just make sure that you understand how to do this one here. Let me just draw another direction. I am going to do a direction from this one here to this one here. Okay, all right, so I didn't start from the origin. I start from the top of that point. And first thing you do is to define the point coordinate. This one will be x equal to 0, y equal to 0, and z equal to 1. And this point here, which is the midpoint of this h, and that is going to have the x equal to what? And should be 1/2. And y will be equal to 1. And z is equal to 1. And we're going to do the subtraction by the head minus the tail. So head 1/2 minus 0. And the middle one is 1 minus 0. And the last one is going to be 1 minus 1. So this result for this will be 1/2, 1, and 0. Now the last step is that we're going to make it into all integer. We multiply it by 2. We got 1, 2, and 0. And this is our direction with the square bracket. This is how we find the direction. So in that arrow, that represents the direction 1, 2, 0. Now, there's another idea which is called the family. So what is the family? That means you have the same direction, and the number might not be the same, but they actually represent the same direction. But how could that happen? Let me just draw another line here to show you why that has a case that you're going to have the same direction. Okay, so I have a yellow line on the top. I have a red line at the bottom. The red line at the bottom also connect to the edge at the bottom line at the midpoint of that edge. If you look at that, this two direction actually is the same. It's just at a different layer, but they have the same direction. Okay, now if we repeat the same process, try to find the direction, which I can define the first point. This is a 0. This is a 0, 0, 0. This one here is going to be 1/2 and 1 and 0. And then we use the subtraction. We got 1/2, 1 and 0, right? And then you multiply by 2. Then you got the direction of the red color, which is 1, 2, and 0. So this is a direction of 1 to 0. However, even though they are at a different plane, but they are the same, right? Which means you can define origin by yourself. Any point will be fine, but the direction is always the same direction. Doesn't matter where you define your origin, they are going to be the same. So if you follow this instruction, then you can find out the direction from this way. There's another case, which is that you can see if your direction to be negative, what happened if that is a negative? If that is a negative, which is this one and here, you're going to put a bar on top of the number to represent negative. Okay, so that's how we define a negative. That just simply tell you the direction of the arrow is toward to the positive direction and negative direction. Now here is the family things. Okay, now, so the previous one I show you the direction, which is the same, right? But you can think about that direction in the several different ways. Let me just use this red color to draw several lines here. I'm creating a direction like this. I create another direction like this. And I do another direction like this. These actually are all the same direction. You just simply rotate the unit cell. Then you will find out, well, they simply represent the same direction, right? They are all diagonal of the surface of this unit cell. And believe it or not, if you repeat what I did previously, and you're going to find the number, and that number is going to be the same, but they arrange in different order, just like this, just like this. And sometimes they might be negative, was because when you define, let's say you define origin to be here. Now, if you define origin to be here, then it will be negative. Or you define the origin to be at the behind this. So all these things will be the same. And then we call this as a family. And the way we identify this as a family is we use angle bracket for direction family. Family of the direction use angle bracket. Okay, this one here, this one here. Okay, so remember this. Direction, square bracket, family of direction, angle bracket. And then on top of that, we're going to add another thing, which is the plane. So I'm going to change this one to the plane. Okay, so the Miller indices also define a plane. When you define a plane, you know, we run out of the symbol. Now we use the parenthesis. So when we use the parenthesis, that is representing plane. That is plane. So this is the way that we represent a plane. Parenthesis. Square bracket, angle. Well, square bracket is the direction. Angle bracket is the family of direction. Parenthesis is plane. Can you have a family of plane? And yes, a family of the plane, and we use the curved parenthesis. So this is a family plane. So that is how we define it out. Now, the plane has a very different way to define, and there's several different stages. Let me just show you how we define that in this example. The first thing you need to do is sometimes you have to move the origin. When are you going to move the origin? If your plane happen to go across the origin, you have to shift it such that the plane is not going to cross, not going to pass through the origin. Okay, so in this case, the blue color plane is the plane that we try to define for this unit cell. So there's no intersection. If we define this as our origin, this is our origin. Oops. So this is our origin. So it's not intercepting with that. So we don't need to do anything. The second thing that you do is to find the interception to each one of the axes. So first you look at the x. So here is the x-axis, right? This is the x-axis. It intercepts at A. So that's why we put A here. Then you look at the y-axis. Y-axis interception is B, so we put B here. And then we look at the interception on the z-axis. Now the z-axis is weird because this plane is parallel to that, so it's never going to intercept. When they never intercept, you put infinity, so that will be infinity. Now we don't write simply say A, B, and infinity. Instead, we do another way to represent that. We take the receptacle of the number. So you take the receptacle, you have 1 over A, 1 over B, 1 over infinity. And what is 1 over infinity? 1 divided by infinity is equal to 0. So we make that one goes to 0. And if A and B happen to be 1, and then you're going to have a 1 and 1 and 0. Now, if that number happen to be the number that we can find a common integer between those numbers, let's say, for example, you have the final result to be 5, 4, 2, and 0. I can divide this number by 2 and still give me an integer, right? So we want a simplest integer to represent the plane. So if you divide by 2, I will get 210, and 210 is still going to be the same as the 420, but we don't use 420, we use 210. And then we put the parentheses to represent this is a plane. Okay, now in this case, because it's 110, so there's nothing you need to divide with because it's already a simplest one. So you use the 1 and 0. So that is the plane. Let's look at the second example over here. So the second example, you can see the red color plane. First thing you don't need to do because it doesn't go across the origin. It's at the front of the origin, right? Then you find an interception. So interception. And you look at the x. In the x, it's about a half. In the y, it's at the 1 unit. In the Z, again, is go to infinity. Well, sorry, in the Y, that doesn't intercept. So it also go to the infinity, right? This plane goes forever, but it never intercept the y-axis. So this go to infinity, Z go to infinity. You take the reciprocal of that, and you find the number after the reciprocal. Then you try to find if you need to reduce that or not. Okay, so in this case, we don't do the reduction for if you only have a 1 or 2. Actually, the previous one probably I shouldn't do the unless all three number are all like a non-zero. If they are there's like a 1 that's 0, then you don't do a reduction. But if that if they are all integer, then you have to find the smallest integer to be the plane representation. But this could be optional, so you can still write like 200. You can still keep the larger number instead of make it to the simplest one. Okay, there's another one that you can watch the slide. I'm not going to repeat that. And the family of the plane that we use the curved parentheses to represent that. Now, not all the plane only represent by 3 numbers. When you work on the HCP, we actually have a 4 direction. Now, you might wonder, how could we have 4 direction? Well, if you represent things in a cubic, yes, you have X, Y, and Z. But when we define the hexagonal shape, because it has 6 sides, and the origin at the center of this hexagonal, then we have a 1 axis go in this direction. We have another axis go this direction. We have third axis go this direction, and the last axis will be the axis go in and out of this center point. So in that case, we have 4 different directions instead of 3. That's why you're going to see 4 numbers instead of 3 numbers. So that is the case for this crystal structure HCP. And that's why you are going to see this 4 number at the very bottom. Okay, I want to just like a very brief talk about the X-ray diffraction. If you watch the video, Professor Wang is an expert in this field. I know his master was working on these things before. And the diffraction, you should learn this one from the physics. And the main idea of this is this picture over here. If you shine the X-ray to the atom, where the element has several different atoms laid with a very periodic structure. And this representation has like 2 layers. If you have 2 planes and you shine an X-ray, and the ray will be diffracted, and when they diffract it, they go to the detector. The detector will detect how much of the X-ray coming through by bouncing back from the atom, right? So when they bounce back, it depends on the distance of these 2 layers, the D. Then you might have a case to be constructive. You might have a case to be destructive. If you have a constructive, then you're going to get a very big signal. And when they have a big signal, and when you put some kind of detector, the detector is going to give you a peak. So this is what we call the constructive. Constructive meaning the peak meets with the peak, right? So And that depends on the angle. So if you learn physics, then you pretty much know how we deal with the light interference. And this is actually coming out from the same idea. The purpose for this X-ray diffraction is, if we know the structure of the atom, now we know each layer, how they lay in some kind of pattern, right? It could be a BCC, HCP, or FCC. Their distance between the plane will be related to their radius. And by knowing that, then we will be able to find out what kind of element that is. Because there's only a certain place you're going to have a constructive refraction. And so when you do the experiment, you're going to make the X-ray to go sweep from a certain angle. Each one of the angle is going to give you a different kind of signal. And certain signal will be picked up by certain direction or certain plane. So in this picture, you can see that you have an iron. And this iron is not like a regular iron. This is what we call the alpha iron. There's several different iron. They arrange it in different way. So iron, even though that is an iron, you might have a BCC, you might have an FCC, depends on the type of iron. If this is an alpha iron, then you use the X-ray, they give you this kind of things. The result is the red color peaks that you see. And each one of the peak represent a plane. Okay, represent a plane. And it will pick up some signal, and that will tell you what kind of structure that is. And we will be able to find out what kind of element that is. So when you do the homework, then you're going to have this kind of problem. And there's an example in the textbook. I encourage you to read that example and work on those homework. And you are also going to have a problem about the X-ray diffraction to understand how we actually apply several things that we talked about before. We talk about how you relate the lattice length to the radius. We talk about the different crystal structure. And now we look at how can you use the X-ray diffraction to find out the element. All these are related. And how do you define the direction? How do you define the angle? These are all combined into the last one, the X-ray diffraction application. So make sure that you work on the example in the textbook of the last one, and we will go through some example on Thursday as well. So I will calculate the density of the element. We will work on some more example on defining the point, coordinate, direction, plane. We will also work on the X-ray diffraction on Thursday. Okay, so that is the main content of this chapter. And again, I want to remind you, our lab for the coming Friday is going to be a dry lab. You don't have to come to school. And we meet 9 o'clock in the morning from Zoom. I will send out the link. And please remember to come to join us. Okay, any question? Anybody with me today? Oh, yeah. Julio and John.
Yep, here.
Okay, I'm going to